Hello, everybody. My name's Neil Stevenson, and I'm going to be talking today about data having a half-life and what on earth that means in connection with financial applications. What I mean by half-life is it comes from atomic physics that certain atomic particles degrade over time, and it's how long does it take to lose half its value, half its worth. So a little bit about me. My name's Neil Stevenson. There's my email address if you want to send me any questions afterwards. I'm principal architect at Hazelcast. Many of you will be familiar with Hazelcast. Generally, most people think of it as a caching product. The fundamental thing I want to stress today is it's a data grid with streaming capabilities. That's an awful lot more than simple caching. And integrated streaming is the key feature of today. That's the kind of big thing that kind of sets it apart. But you've got querying, you've got caching if you want caching. It runs in the cloud. You've got security, all the kind of nice to have features that you're going to need. But let's kind of start with the problem. What's some real world problems that we're going to have to deal with, and obviously the solutions to the same. So because we're looking at finance, let's start with investment banking. So we're going to have an investment banking system. There's various things we might do, but today we're going to be looking at a stream of trades on the stock market. We want to know what is going on in the markets because we wish to somehow exploit this. It might be we want to put buy and sell orders in. It might be we're looking at how we manage our cash reserves, various parts. But fundamentally, what we kind of want to see is what's going on in the market, what's going on in the market right now, because we want to make decisions based upon that. Is there been lots of activity, or is it just a few big orders going through? Those kind of questions. Now it's described here on the left of this slide as investment banking, but if you imagine, let's pick another problem domain, e-commerce, a lot of the problems are the same and therefore so are the solutions. You wanted to know, how many orders are coming through. That's what trade is. What's selling well? What are we going to do about it? Well, that's kind of going to depend more on our business, but fundamentally that's what we want to know. So if we kind of take an even higher level view of this, what we want to know is when did we last sell something? What do we sell it for? What was it? What time did we sell it? When did we sell it? What price did we sell it for? And kind of more useful as well is kind of, well, how many of those have we been selling? How many of those have we been buying? And those are kind of fundamental questions, but they're also fundamentally different. The last item is just a single item, a singleton. That's not too difficult to keep track of. Whereas the second question is much more of an aggregation. It's a derived state. How much of this have we sold is how much has been featuring in multiple data items. We're looking for a derivation there, and that's quite a different thing entirely. And from a business user's perspective, we want to see both. We want to see them both in the same place, and we want to see them both at the same time because we're demanding business users. This is what we want to know. So if we look at a kind of traditional solution to this problem, our stock market trades are coming in from the outside world. We don't have a direct connection. We use, in this case, a Kafka topic, but there's going to be some sort of event bus, some sort of buffering system that separates one system from the other and provides that kind of connectivity, essentially. So we've got our trades coming in from somewhere. Don't really care where, but it's pretty obvious where it's going to be. And we need to store those for various requirements, and that's what we'll use a database for. Now, when we're processing those trades and storing them in the database, it's pretty easy to keep the kind of last price. But what's not so easy is the running total. So if we're storing them in a database and we do that analysis on the database, then we've essentially turned that stream of events into a batch. because analysis on a database essentially means a table scan. We've got to scan all the items with a specific stock symbol. Now, index might help a little, but fundamentally that's scanning multiple things to do some sort of aggregation function, a sum on it. And that's not really what databases are best at. So what we've done is we've introduced multiple layers of latency. There's the time to save it into the database, which we're relying upon for the next result, which is where we do the aggregation in the database. And then we get the aggregation result out of the database and into this web server so that end users can browse it. And all of these aggregations essentially boil down, all these latency essentially boil down to delay. So the end result to the end user could be hours behind what's actually happening in the market, certainly many, many minutes. And that's not good, not good enough. So really the kind of problem is actually we're using persistence in the data store for two things. You know, we want to retain these trades forever or however long, and that's fine. And in analyzing it, there is not going to be good. It's not going to run fast enough. We want to know what's the total trade volume. Well, that's the total of all the trades. And, you know, is it like lots of small orders? Is it lots of home investors, or is it some big institutional investors moving the market? We need to know these things. And we need to know it now, quickly. So the process flow we have for the Hazelcast solution is a bit different. Now, we're still going to have this database somewhere. We're still going to store the trades. We haven't just not shown that in the diagram because that's now a kind of separate concern. So we have a Kafka topic that contains our series of trades. We can simply upload that into the Hazelcast data grid and cache those trades. So we can store every trade that's come in our Hazelcast data grid and make them available to a web server. We might index it so we can search them faster. But fundamentally, all the trades are stored in memory. The end user can browse them. That's fine. But the more important part is we can be running predetermined queries against those trade topics as we're ingesting them to produce live aggregations. So every time a trade comes in on a Kafka topic, we're pulling that into memory and analyzing it at the same time off the same input source. So we've got the simple result, which is the trade cache, which is essentially the input becomes the output. And we've got the derived result, which is where the input feeds into the output. The output's updated every time for the input. So that's a kind of push base. Every time a trade appears, it pushed through the streaming engine into the results cache and is available for a web server. So it's happening essentially real time, certainly faster than a human can deal with. And it's all kind of all the nice parts of Hazelcast. You can scale it across multiple machines. You've got resilience, all the kind of securability, all the kind of nice to have kind of stuff. But that's the architecture. If we drill into it in a little bit more detail, anybody that's familiar with Unix pipelines has kind of come across the idea of job stages and the output of ls pipes through grep, pipes through sed, pipes through awk, whatever. So a stage goes to a stage, goes to a stage, and each of those stages has got input that's coming from upstream and it doesn't care or see where, an output that's going to downstream. And again, it doesn't have any visibility where, it's just an intermediate that's doing a bit of processing. So this is what our processing is here. We're uploading from a Kafka topic. We're doing a lookup to a Hazelcast map because some of the stock symbols are in delinquent or bankrupt state, and we just want to filter those out. We're not interested in those. Now, that's not an attribute that's on the trade itself. That's an attribute stock symbol. So we need to do that reference data lookup. Then we want to be grouping them by the stock symbol because that's the foreign key on the trade, and then aggregate based on that foreign key. So every time there's a trade for stock AAA, we update the counter for AAA. And every time there's a trade for stock BBBB, we update the counter for BBBB. And those are available in the results cache for the end user. And they change every time the input comes in, the cache is updated with new values. This is the actual code. This is code I'll show you in the demo later on. I've colored it in yellow. There's just 5 steps. The first step, the ingest step, the read from, is just a pre-built. You just say, well, just pull in from Kafka, and there's the Kafka topic name. And the last stage, the sync stage or the save stage, is just one of the pre-builts. We're saving it into a Hazelcast map that's called aggregate query _ results. The intermediate steps are kind of the bits that are interesting. So this map using map is that look up to that reference data map, the symbols map, and we're just doing a check. Is the financial status normal? In which case we allow the trade through. And if it's not, we null it out and it gets discarded. So as I mentioned, we're not interested in stop symbols in specific statuses that aren't normal. You do that grouping based on the trade symbol, which is the foreign key, because trades are keyed by an ID, which is just a sequence number. And then we're doing a three-way aggregation. We're actually keeping 3 running totals per trade, per stock symbol, rather. So we're just keeping the count, how many have there been. We're doing the trade volume, which is the price times the quantity added onto a counter. And we're just keeping the latest price. So those are the kind of steps in my job pipeline. Not a lot of coding. If you're not a coder, you could do it with SQL. If you'd rather, it's a slightly different SQL query, but you can be joining Kafka topics against maps and things. And conceptually, this is kind of how it pans out. The green box is meant to represent a host machine. So my Kafka topic is read in, etc. But if I've got 2 host machines, I just run 2 cloned copies of my processing job. So my input is now split across 2 machines, so I can process it at twice the rate. If that's not fast enough, I can go to 3 machines or 4 machines or however many machines are deemed necessary to hit my SLAs. So I can change the number of copies of my processing job, number of clone copies of my processing job, according to my input volumes. Architecturally, the way I'm going to demonstrate in a second is my streaming engine, my jet engine, and my data grid, the IMDG part, run in the same process. It's one JVM, it's got both parts in it, and that's simple. So in this diagram, I might have my Kafka topics partitioned into 3, and my Hazelcast is running across 4 machines, producing result for the web client. That's just the easiest way to do it. So the data grid is doing the storage of the trades. And it might be that you decide, well, actually, let's keep 2 days worth of trades. So you're going to need double the storage requirement because you're now keeping 2 days worth of trades rather than 1. But you don't need double the processing need because you're still getting 1 day's worth of trades in per day. So you might choose to scale the streaming engine and the storage engine separately. If you decide you're going to keep many, many days, you know, it's a bit of extra granularity for a bit of extra work. So you can do whichever way suits. But today I'm doing it the earlier way where they're just in the same process. A little shout out to how fast this can be, because this is the kind of important thing is around your data freshness. There's a benchmark run by the University of Portland called Nextmark. We've run that recently. If you go to blogs.hazelcast.com, you can find that bit more detail on this. But we ran 1 billion events per second through a Hazelcast cluster. That's like going to be more than you need, I would imagine. And it wasn't a big cluster. It was like 45 nodes on AWS. And these were C5-4X large machines, which aren't large machines. They've got, well, they aren't particularly large. They've got 16 CPUs and 32 gigabytes of RAM. It's not like a lot, 68 cents an hour each. You know, so 45 node clusters, $31 an hour. You know, it doesn't sound like a lot of money to process 1 billion events per second. So that's into trillions per hour for $30 nothing. But it's time for demonstration. So I'll go to my web system. So our topic, our messages are on a Kafka topic, which I've called KF_trades. And if we look at the actual messages themselves, these are generated data. I don't have a live connection to the stock market, but it wouldn't really matter if I did. And they're held in JSON format. So trades have got like an ID, which is just a random UUID, or maybe it's a serial one. they've got a timestamp, a stock symbol, a price, a quantity. In the real world, they'd have a few more fields, but fundamentally that's it. It's just a piece of JSON data. So there is my primary key, and here is my foreign key. And if we look at our Hazelcast cluster, on monitoring, it's a cluster of 2. If I look at my end user's dashboard, then what I see is this is my monitoring, my web app monitoring the data grid. So this is the user's perspective of what's going on in the data grid. And hopefully you see some of the prices flash red or green, which basically means the price is going up or the price is going down. And what's important is if you look at the columns, the price column, that's that last price, that's that easy state, the last state. But the volume column is the derived state. That's the difficult state to get. And you'll see that every time the price comes in, the derived state is changing as well. It's happening a little bit fast and obviously a little bit random. But if for the sake of argument, we were interested in whatever this top ships is, then look at the volume, you've just seen it just change. What is going on with there? Well, I might look and see, well, here are all the trades today for the, in reverse order, for the tops shipping company, whatever they do. And perhaps that tells me something. Look at those that trade quantities, perhaps not, but this is the information that kind of business users are going to want. What has been going on in the market? Operationally, this is a 2-node cluster. So let's go and have a look behind the scenes. So if I take my processing job, my aggregation job, that was that piece of Java code I showed you a little bit earlier. If I look at my map using map stage, I can see it's read in 300,000 records and 360 odd thousand records, and 345,000 have come out because it's doing a bit of filtering. And if I wanted to, I can have a look at the maps on my system. This is my storage. So I have 3,000 stock symbols on the NASDAQ, slightly less than 3,000 query results because I've mentioned more than once that I'm filtering some out, and 300,000 trades. And if I look at my 300,000 trades, there's 100-odd thousand on each of 2 processes. Now I want to have a wee look at my data. So if I take my aggregate query results, I can do an SQL query on that. There's pre-coded. So there's our old friend tops, TOPS. We've had, there's a 3-tuple that's come out of the aggregate query, which if you remember, it was, there's the count. So count of 118, there's been 118 trades for that stock symbol. There's the running total on the volume, and there's the last price. If I rerun that query, I might get a slightly different answer, and I haven't got it in order, so I want to do let's just look at tops. So 123 in this price. If I repeat that query, maybe I'll get a different answer. Just depends on luck if there's actually been a trade coming for that thing. There we go. Now 124. And if I wanted to have a look at my stock symbols, I can do the same on my stock symbols. And I can see that my stock symbols have various status column was the one I was interested in, financial status, and most of them are in normal, but you can see that some of them aren't in normal. So this is a 2-node cluster, and that will process at a certain rate. And some days the market gets a bit busier. So I will do a scale up on my PaaS layer. My PaaS layer is Kubernetes. So basically, I just ask Kubernetes to go from however many replicas it has, which was is running 2 replicas out of 2 requested. And now if I look at it, it's running 2 replicas and 3 requested. So the PaaS layer will go off and find another machine and add that to my Hazelcast cluster. Now, this query, this is kind of your pre-built one. This is the one that the user is going to want to know about all the time. But the whole kind of point of this is that driving of insights. And now we're going to want to know, well, what's actually happening? And this is where you do your kind of ad hoc queries. So this result is essentially push-based. As data arrives, it flows through the system and updates on screen. Now I want to do a kind of pool-based one, and I'm going to say, well, let's go and query what's currently on the Kafka topic and do a left join with our symbols. Basically doing a lookup of data that's not in Hazelcast, joining it against data that is in Hazelcast. And this tells me that for whatever that stock symbol WATT is, it's in capital market, market category, normal status. This was the last trade timestamp or whatever. So I've been doing that. In the background, my PAS layer has changed my cluster to 3. And I see 3 members here. And if I go and look at my maps, I'll now see that we still have the same number of stock symbols coming out, but now we have a slightly larger number of trades because they've been coming in all the time while I've been talking, and now they're spread across 4 machines. So I forgot to mention it, but when I had, they're spread across 3 machines. When I had 2 machines, it was like 180,000, and if perhaps that was using up capacity, I'm going to need more machines, so I just add a 3rd machine, and they spread across the 3 machines, and each machine takes a roughly equal load, and that's how you hit your SLAs. You just keep adding and removing just to adjust to changes in demand. And you do this while the system runs. There's no kind of outages or any of that kind of stuff, because you don't want outages. So just to kind of close off onto the summary. So back to atomic physics. Uranium-242 has a half-life of 16 minutes. I've been talking for more than 16 minutes. So if we had any uranium-242, which would probably be a bad idea, we've lost half of it. It's degraded already. And that's what I mean by half-life. The value of this information decreases over time. It's most useful as soon as you kind of produce it. And that's what I mean by insights are perishable. You derive some data about your system that, we should be buying or we should be selling. That's got the most value the sooner you can do it. The longer you take to calculate that information, the less chance it's going to be right. So really what you want to do is every time the input changes, the output updates. You want it continuous. You don't want to go and scan. No, it's as it arrives. You've got an event base coming in. You want event base going out. Every time the input changes, the output changes. And it kind of follows on from that ETL just won't cut it for that use. ETL still got its uses, but if you're doing something time critical, just give up on it, because the idea that you go and fetch the data from somewhere else, you drag it across the network from out of whatever store you have, and probably that store will be like a persistent store that will be slow to extract from. Then you've got to pull it across the network. Then you're doing your analyzation and analysis and then saving it somewhere. You're just introducing latency in every step, and it all accumulates, and your results are going to be slow to produce. And if they're slow to produce, it's kind of like telling you what the weather was 10 minutes ago or an hour ago. It's not as useful as knowing what it is right now. And if you're doing any kind of trading and your competitors know what it is right now, they're going to beat you. It's as simple as that. But you should know that anyway. So that's it. So what it boils down to is you've got to be doing your processing as your data arrives. Every time the input changes, you've got to update the output. And that's me.
Neil, welcome. Thank you very much for the great talk.
Thank you.
All right. Well, we've had some great questions already through the chat function. If there is any questions that anyone has had that you haven't had an opportunity to ask yet, certainly enter those into the chat message, and we'll go ahead and ask those to Neil. There was a couple questions I think that we wanted to elaborate a little bit more that were going on during the session. So let's go ahead and hit those up, Neil. How does that sound?
Yeah, that's fine. So I've seen 3 that I think were kind of came up that I didn't quite answer. One that's just come in, and 2 that have come up earlier. So if I just scroll back and double check. So one of the questions was, does each of the Hazelcast nodes maintain an individual counter for each stock symbol? So basically, if you've got a 2-node cluster or a 3-node cluster, as I had there, and we had a stock symbol XXXXX, do we have one counter for that, or do we have one on each machine? And the way we have it set up on that demo is there's only one counter and you route trades based on the stock symbol so that they all end up on the node that has that counter. So node 1 might have the counter for XXX, and node 2 might have the counter for YYY, and you use that foreign key to route data from place to place. Now, that's kind of not a free lunch, because route data from place to place means you're sending it from one machine to another. So that go across the network thing that I'm not keen on. So one of the things you can kind of do is you can maintain subtotals. So all the XXXs that node 1 has seen, and then periodically emit that to a central counter. So do a kind of subtotal that goes to a grand total. But if it's going to a grand total, you can't do that all the time, because otherwise you've not achieved anything by having a subtotal. So if you have a single grand total, you can update it all the time. In that case, I had 1,500 stock symbols each on 2 machines, because there was about 3,000 in total. So all I'm really saying is, can my machine support 1,500 counters updating concurrently? And if it can't, I'll have twice as many machines, and then it's only got to do 750 counters. You can throw hardware at it as long as you can partition your input. So if all your stocks are for the one symbol, then that's not going to work out nicely. Now, generally, you expect a little bit of variation, but not a kind of huge variation. So that was one question.
We had one from Alexi. Now, what if the eventual consistency is not enough? For instance, for the price change, we have to calculate the Greeks for various instruments. Is there a way to solve this within the streaming engines? And if yes, how can Hazelcast help with that?
Yeah, so the sort of is. So what you're kind of saying is, you've got a price change and it might affect, say, 2 portfolios, and they're on 2 different machines, or 10 portfolios are on 5 machines. So that change doesn't have to be sent to one machine. You can do a broadcast and send that price change to all machines and say, well, look, this item has changed and you all need to know about it, and you can revalue all affected portfolios. But to do that is really kind of pushing the bounds of compute, because it's like, well, how often can you revalue a portfolio? You know, if what you're saying is you've got to do 10 milliseconds of processing and the price changes every 10 milliseconds, it can only just keep up. If the price starts changing more rapidly than that, you're stuck. There's no way you can do a live update if it's coming in faster than you can cope with. When Hazelcast does that workload partitioning, it's essentially based on the number of CPUs. So you can have, 10 CPUs can run it 5 times the rate of 2 CPUs. But ultimately, you cannot partition that work across everything. So if you've got a portfolio, you need to have all the data for that portfolio in one place. So you can only do that at certain rates. So, and that's kind of not really a Hazelcast restriction. How fast can you update a portfolio? Distributing the work across multiple CPUs helps, as long as the rate it comes in doesn't exceed the rate you can do it. Is that enough of an answer? I don't want to kind of...
That's great. No, yeah, thank you.
And then we had another one down at the bottom. So what's the difference to Kafka streams? Well, kind of 2 parts. So one is kind of Kafka streams is really just a kind of Kafka-based solution. So where we were doing that there is we were enriching data from other sources. So you could be pulling in from file systems, or what I call a map is like a Hazelcast cache. So that kind of enrichment depends on being able to access other data sources. And if you're a user, you just don't care where that data is. You just want the answer out. So you're saying, do this, do this. And then also you've got to kind of consider the performance aspect is, how fast is your business going to need to be? I mentioned the billion events per second. That's because it's memory-based. Disk-based systems won't be as fast as memory-based systems. Well, you might not have a billion events per second yet, or perhaps ever. But then the faster you can do it, the less hardware you need. So there's like a ROI kind of side to it as well.
Great, thank you. We've got a few more minutes for questions. So again, if you have any questions for Neil, certainly type those into the chat. Another one that we've got, does ETL still have a part to play in the landscape?
Oh yeah, yeah. It's just slow, you know. So the thing is kind of business users, if they see they can get something now, they're not going to wait for overnight. There'll be certain things where if you're doing like regulatory reporting, the current need might be, you know, produce this report for the morning. And that's fine, but you kind of might have internal reporting where you want to know kind of what's happening more and more frequently. And it might be that, you know, you only have to tell the outside world once a day, but if you as a bank knew what was happening once an hour, say, you could be more efficient with your investments. And then once it's once an hour, well, it's going to be 15 minutes. And once it's 15 minutes, we're going to want 5 minutes. And once it's 5 minutes, we're going to want 1 minute. Down to the point, on that demo, the screen was kind of refreshing. I think the end-to-end time we measured it on two cheap boxes was like 3 milliseconds or something. The human eye can't keep up that fast. So if you're like a trader watching that screen, the data's coming in more than fast enough. So ETL has still got its place, but it's where time isn't relevant massively or competitively. And perhaps that will change over time. It's the moving data from place to place is the penalty. If you're trying to get it out of a relational database, there's all sorts of kind of hidden costs because you might have it in a table and you've got to use something like Hibernate to reformat it into something else, into the format you want. So it's not just an extract. There's that transformation part, which is you know, CPU cost. And kind of, you know, don't obsess about the network thing. That's just moving something from place to place. If you then do heavy computation, then the moving it is maybe only a small percentage. So, you know, work on what problem you can solve.
Sure. Now, how and where does caching help?
Caching really helps on speed. So something like those I mentioned on that thing where it's looking up stock symbols and it's saying, is this stock symbol bankrupt, delinquent, deficient in some sort of unpleasant state? That data can be cached because that data hardly ever changes. And when it does change, you don't really care about how rapidly you get your copy up to date. So all we're really saying is drop some records because we're not interested in those trades. Well, if it's like a stock symbol, they're not going to be changing from live to bankrupt status and then backwards and forwards all the time. You know, so being able to keep a copy of that data adjacent to where your stream processor is doing, which is what we were doing there, in the same JVM means you don't have that network and you've got thousands coming in. You're just doing a local reference data lookup. That reference data is essentially can be duplicated in other machines. They're only just looking at their own copy. And they're all copies of something else that doesn't change frequently. So that's kind of where caching is kind of good. But caching kind of also, if you call it caching, it kind of twists where you think that data lives. You know, it's like, well, data in Hazelcast, you might call it a cache, but you can change it. And then that's not really what a cache is. That's just another copy of your data. You've got data in memory, data that's on a disk, data that then is also on the tape. And it, you know, so where is that data? And it's in multiple other systems as well. So you find in big enterprises, data exists in multiple places at different points in its life. So it's difficult to actually say what's a cache of what. If you think of cache, you think of a convenient copy that's static, and that's maybe not what you're going to do. You maybe use your disks just for kind of legal and audit purposes and your memory copy for rapid processing.
Great, thanks. All right, does all the data need to be held in memory? Now, if not, how do you identify the most useful data?
Well, it's best if you can, because if you've got to go and fetch it on demand, it's going to be a speed bump, essentially. But there's like a cost to that, you know. So if you take, for example, that stocks information, so the output of that demo was here's today's trades. You might want to keep yesterday's trades and last week's trades in memory. So you might want to keep 10 days worth. Well, that's 10 times as much storage. You might want to keep 20 days worth. And suddenly there comes a point where you're not kind of really needing it. So you can kind of page it in on demand to be more kind of cost effective. So if you imagine you went to your online bank and you looked up your transactions and you could see this month's transactions immediately. That will be good. If last month's transactions were immediate, well, that would be useful as well, but would you really care if it took a few seconds to go and load last month's transactions? It's a kind of user experience that people are kind of keen on. Well, not keen on, but tolerant of. Go and see last year's transactions. Well, it'll take a few seconds to bring them back in. But yeah, I'm fine with that. That's not going to make me change bank. So it's a cost benefit kind of thing. You can hold, terabytes, but you got to pay for it. So, only the data that has the most value. And then the way you identify that is that kind of least recently used kind of data. You can page out stuff that you're not using. Have you read it? Have you updated it? Well, if you haven't, you don't need it. So the more you can hold, the better. But economics comes in. You've got to pay for this hardware. So
great. Follow up from Alexei from an earlier question. So he said, "Thank you for answering about the consistency. My question is more about to be able to have transactions because the Greek values may come in different orders from the different price events. The total data from total delta rather from the same underlying instrument may just jump up and down substantially."
Yeah. So you're kind of asking about kind of transactional processing. So with stream processing, you kind of have, you got to be careful with transactionality because it depends on what your sources and sinks are capable of. So if you were doing something like reading from a Kafka topic and you have to kind of stop and restart because you're doing maintenance or something, you can kind of restart from a specific offset. If you were kind of connected to like a WebSocket or a web server and you stop processing it for a while and you restart, we'll probably have a gap in your input. And it's the same on the output side. Can you cope with that kind of transactional behavior where everything is done kind of atomically, but you've got to consume something and then perhaps not consume it? Time is almost coming up. The bit about Greek, so really you're looking for multiple inputs to have an atomic update on a data record, which essentially is a join. So you can join two streams together to produce a join stream, but you've got to be careful if these are both infinite, then you have no endpoint. It's like, so you've got to set a kind of a window on two streams and say, let's take the last 5 seconds of this and the last 2 seconds of this and see if we can combine them together. And picking that window, the bigger the window, the more you've got to join, the more Cartesian product combinations. And the longer you've got to wait for a window to fill up. And, there's a lot of kind of moving parts to stream processing. So the idea that you can just kind of join things, well, I maybe made it look easy on the demo, but there's, a lot of reality that if you wanted to say, do something like take the average of an infinite stream, well, the average is you sum them all up and you divide them by the count. And if it's infinite, then you don't know what the count is. So some of those operations aren't logical and you have to break it into windows. And those windows might be kind of overlapping. You might say the last 10 minutes advanced by 1 minute. So you go minute 1 to 10, minute 2 to 11, 3 to 12, and so on. So some of that data might feature in more than one window. But yeah, there's a lot of complexity once you get into the detail. It's not like a kind of, to get it right, you need to kind of have your kind of best practices around you. Performance is what it's about, and that's, don't just kind of sit down and have a first bash and it's easy. It doesn't necessarily end up as a lot of lines of code. It's just which lines in which sequence. So something like that grouping key is moving data from host to host, and that's the kind of thing you want to postpone down the pipeline so that you get as much work done and then reduce the amount of data volume before you do any kind of transmission, just an efficiency thing. But if you do it the other way around, you can run it through 1,000 unit tests and it won't go anything wrong. It just won't be as tweaked, as optimized.
Excellent. Well, thank you, Neil. Thank you all for all the great questions that came in today. Thank you, Neil, again, for taking some time to visit with us. If you've got any additional questions, certainly feel free to scroll down the page. So there's going to be some great content from Hazelcast that's available on this page, as well as a chat that you can have a live interaction with some of the staff. Otherwise, thank you all so much for joining. Thanks for the questions. And thanks again, Neil, for taking some time to visit with us today.
Thank you.